Okay, well, welcome back to Biochemistry Review, BCH4053 at FSU. Today I'm going to be talking about the inhibition of ATP. Okay. So ATP, the ETC cycle, which generates ATP, has 5 complexes, but 6 different ways that we can inhibit it. So first we can inhibit it at complex 1. We can inhibit it at complex 2, complex 3, complex 4, and complex 5. We can also inhibit the membrane, or this whole system, by disrupting the membrane, because as we know, that protons that flow up need to flow back down to form ATP synthase. So what if we just make a hole in that? Well, I'll go over that in a second, but first we'll talk about the moles generated, or the amount of it. I should say molecules, not moles, I apologize. The molecules that are able to be generated through one cycle of this ETC, right? So it takes 4 protons to generate 1 ATP molecule in ETC. Now, if we look at the ETC cycle, I'm pumping up 4 hydrogens at 1, I'm pumping up 4 at 3, and I'm pumping up 2 at 4, right? 3 at 4, 4 at 4 pumps up 2. So I'm generating a total of 10 protons, which gives me 2.5 molecules of ATP on a good day, right? But what if we give it a bad day? What if we decide that we need to inhibit ATP? Well, there's a couple things we can do. First, let me draw this out. 2.5, 1.8, ascorbate, or vitamin C, which can add electrons here. Okay, so the first type of inhibitors are complex 1 inhibitors. Okay, and that is your rotenone, pyridine, amytal, mercurials, and dimerol. My handwriting's not amazing. Let me write that out bigger. Rotenone, amytal, oops. And dimerol. Okay. So, in this exam, these are the main ones you need to know. And these are complex 1 inhibitors. Complex 1 is your nicotinamide to coenzyme Q, oxidoreductase. So what happens, make sure you get that down, and you can maybe make a little mnemonic. I like rainbow puppies are magical dogs. This is one of my favorite. Okay, so this is a complex 1 inhibitor. So what happens if we inhibit this complex right here? Well, how do we generate ATP? We have these protons, right? So what if we block this proton flow right here? Well, we're only going to be left with these 6 over here. And we know that it takes 4 to generate 1 ATP. So 6 divided by 4. We're going to create 1.5 ATP. Okay? And that's not going to come from NADH at all. It's only going to come from FADH2. And also ascorbate, but we're talking about how much we can generate at one time. We're usually talking about 1 substrate going through the cycle. Okay. Next. Is complex 2 inhibitors. Now, for this exam, all you need to know is eno-trifluoroacetone. And you will need to know, what is it? acetone and carboxyl right there. Yeah. Sorry about that. Carboxyl, you can remember this by that 2 has 2. So these are 2 inhibitors, and they're going to inhibit complex 2. But if we inhibit complex 2, we still have NADH. We can go through complex 1, complex 3, and complex 4. As we remember, complex 2 does not actually donate any protons to the intermembrane space right here, right? We're still going to have 4, 4, and 2. And it's not really going to, it's going to still give us 2.5 ATP units. So yeah, that's complex 2, or succinate to coenzyme Q oxidative reductase inhibitors. Now we look at complex 3. Complex 3. So this is, it's going to get a little more tricky here. When we have complex 3, we talk about this, we have to look at what's happening upstream of where we are, right? So we know that 4 is going through here, and even if we block off this, we still have 4, 4, 2. But if we're talking about complex 3, which has 2 that you know for this exam, oligo mycin and antimycin, pretty easy to remember. What's happening here is we're blocking off this, right? So we can only get electrons from a ascorbate, because if you think about it, coenzyme Q, which is donating electrons, can't donate to 3, which then can't send over electrons to cytochrome C except for our ascorbate, right? So the issue is that, we still have like maybe this pump out once, these electrons from here, but we're blocking off this compound here, or 3 here. It's not being able to donate any protons, and we're stuck. We're only left with the ascorbate at 0.5, and we cannot send any more electrons. All the electrons are going to get kind of backfilled here. They're not going to be able to actually oxidize FADH and NADH the same way, because it's a cycle that goes through here. So we're only going to be left with the 0.5 ATP from complex 3. Okay, so that's complex 3 inhibitors. Let's look at complex 4 inhibitors, which is cytochrome C oxidase. So as we know, that cytochrome C is the first thing that goes in there. If we block off this, electrons can't flow from 4 to 5. We're pumping all this stuff up, but now they're not flowing from this, but the proton gradient is disrupted. It's going to get stuck. We can't pump this out. Cytochrome C can't come in here. It can't be reduced by 3. So 3 is not going to stop working because it has all these electrons. It can't get rid of them. Same thing's going to happen on 1 and 2. So if we block out 4, this entire cycle ends, and we're left with 0 ATP. And this is why stuff like cyanide, very famously, cyanide, spell that, and carbon monoxide are so deadly. Now you also have to know azides for this test. These are 4 inhibitors. Okay. Now we can talk about some uncouplers and ionophores. So, let me just pause this for a second. Okay, sorry, small mistake. I said that it was antimycin and oligomycin, complex 3, but I made a mistake. Oligomycin is actually an ATP synthetase inhibitor, and one you need to know. There's also DCCD. Both these inhibit ATP synthase. which if you inhibit ATP synthase, well, you can't synthesize ATP, you're left with 0, right? Okay, so sorry about that. Let's talk about uncouplers. Let's talk about ionophore antibiotics. And let's talk about okay, so what's happening here is we have, these do not directly interact with any complex by themselves. You can think of them as disrupting the ETC cycle in general. The easiest one to think about, I would say, would be ionophore antibiotics. So, I don't know if you know what ionophore channels are, but they're like little channels inside the membrane that can send ions back and forth. So, one of the most important things about the electron transport cycle is that it has its proton gradient. So if we disrupt that, there's no proton gradient, there's no reason for protons to go through ATP synthase, and we can't generate any ATP at all. In fact, for all of these, you will generate 0 ATP. Thermogens use ATP not for energy, but for heat. Okay, sorry, wrong distinction. ATP does not get generated as heat from thermogen. Thermogenines also form a pore. In fact, all of these form pores. So that's the main kind of distinction. The main distinction, I apologize, is that uncouplers, you can think of them as creating a channel where everything can flow through. And in this case, the coupler we don't know for the exam is DNP. So basically our protons, they can flow back and forth, and they're chilling, okay? So ionophores, ions, not protons, I apologize. There's gonna be 2 on the exam. There's gonna be mycin, I believe, and gramidin. Let me write that out. If I'm spelling this right, valine, mycin, and gramidin. So these are ionophores, and they work differently. This is a cation transporter generally. And valinomycin specifically transport potassium ions. So let's say we have this right here, and we have some potassium floating around, it's positive. Well, it's going to flow in here, and protons don't want to travel in there. There's all this positive energy, and positive people like to stay away from each other, I suppose. I mean, this is gonna disrupt the membrane. There's no reason for protons to not travel back into the matrix. Okay, thermogenins, similarly, the heat comes in. Sorry, protons come in. And what happens here is the hydrogens that can go through here are now released as heat. And that's the key distinction. It forms another barrier for hydrogens to flow back into the matrix, just like ATP synthase, but instead of ATP synthase, which converts it into ATP, it's just released as heat. So that's where all the energy from the gradient goes. And so for all of these, and for thermogenins, the UCP1, or you might just write it out as thermogenin, uncoupler DNP, ionophore antibiotics, valinomycin, and gramidin. And all of these will cause ETC to break down, and we're left with 0 ATP formed. We break the gradient, we break the formation of ATP. So those are the inhibitors you need to know for the exam, and if she asks you, now you'll know how to deal with them, I suppose. You might ask a question like, I introduce, say, amytal into the ETC. How much ATP can I form? And we know now that ATP blocks complex 1, but complex 2 is still going to be able to provide electrons, and we're going to be left with 1.5 ATP at the end of all. So that's the most important thing you know, and thanks.